मुझे वो लिंक भेजो ना एग्जामिनेशन का।
क्या?
वो एग्जाम का लिंक।
आप मेरे नंबर से लॉगिन कर लो। आपको एक वेब क्लास पे भेजा था ना, उस पे जाओ और मेरे नंबर से लॉगिन करो।
एक मिनट। स्क्रीन शेयरिंग इनेबल कर दो।
किया था अनुश्री?
हाँ एक मिनट। वेब क्लास ना?
व्हाट्सएप पे होगा ना लिंक?
हाँ लेकिन मेरा लैपटॉप है ना, तो इसमें व्हाट्सएप नहीं है। वो कौन सा क्लास ऐप है ना?
हाँ, इस पे क्लिक करो एक बार। फार्मैक ORG कोड है, फार्मैक PHAR MAC 855
नंबर
855 1045 335। um 2059।
ये वाला है ना? GPS 2.0।
हाँ यही है। टेस्ट में जाओ। यूवी। हाँ मास बराबर।
ठीक है, चालू कर दे क्या?
हाँ चालू कर दो, मैंने आपको होस्ट बना दिया। आपका जब हो जाएगा ना तो बस मीटिंग एंड कर देना।
ओके ओके, बस उतना ही करना है ना?
हाँ बस उतना ही करना, रिकॉर्ड करके आराम से, और फिर मुझे ये कर देना, मैसेज कर देना कि हो गया।
रिकॉर्डिंग तो बैकग्राउंड पे चालू ही है ना?
हाँ चालू है, एंड कर देना मीटिंग बस।
ठीक है, ठीक है, थैंक यू।
ओके बाय।
Hello everyone. Today we are going to solve some MCQs regarding mass spectroscopy. So I will help you go about each of these questions individually and give you an idea how to solve them and attempt them logically and using whatever knowledge and information you have gained by studying. And since we have to, there is a negative marking for GPAT, we are going to make it easy. We will approach the easiest question first and attempt them first, and then we will utilize the remaining of our time to attempt the difficult questions, if any, in this test. So let us begin. Move on to question number 1. This is regarding the mass spectroscopy. So which of the following is done normally to convert the sample into a gaseous state? Option A is sample is pressurized. Option B, chemical reactions are made to occur. Option C, sample is heated. And option D, sample is cooled. Now I will tell you the strategy how to eliminate the not so obvious options. So the very obvious or the first option, which is sample is pressurized. Usually when you pressurize a gaseous molecule or any gaseous substance, they usually get compressed into a liquid, like you have your LPG gas. So option A is not at all applicable. By pressurizing the sample, you cannot convert it into a gaseous state. So option A is eliminated. Option B, chemical reactions are made to occur. Even though you might carry out certain chemical reactions, that is not necessary that they will always result in the formation of gases. So the chances that your molecule, without degrading and maintaining the exact integrity, will get converted into a gaseous state by undergoing chemical reactions is not possible. So option B is also eliminated. Now we have option C, sample is heated, and option D, sample is cooled. D can also not be an option because if you're cooling a sample, it is not going to get converted into a gaseous state. So the obvious answer is sample is heated, because when you're heating the sample, as you know, you can, when you're heating or boiling water, there is a production of steam. So similarly, when you're heating any sample, they lose all the moisture or the water molecules entrapped in their entrices, and then the gaseous matter can be released. So any sample can be heated. That means if you're preparing a solution of your analyte, then if you're heating, then there are high chances that the solvent, basically you're going to disperse your analyte in a volatile solvent. So while heating, the volatile solvents gets vaporized, and in among the vapors, your analyte molecules are also traveling into your mass spectrometer. So the option is sample. My option is the correct answer is option C, which is your sample is heated. So let us save and move on to the next question. What are the main criteria on which mass spectrometer is used for? Option A, is it the composition in sample? Option B, the relative mass of atoms? Option C, concentration of elements? And option D, properties of sample. Now the question is very simple. You all know what is mass spectrometry or what is mass spectroscopy. So basically the basic idea of mass spectroscopy is analysis by analyzing the mass of the atoms or the molecules which are present in your analyte. So the main criteria on which mass spectroscopy is based on or is used for is nothing but option B, which is your answer, the relative mass of atoms. Composition in the sample cannot be identified by mass spectrometer. Concentration of elements cannot be identified directly, because indirectly you're going to estimate the concentration based on the mass to charge ratio on the relative mass of the atom. So option C is also not the correct answer. And D, properties of the sample cannot also be detected by mass spectrometer, because the physical properties, whether it is a solid, liquid, or a gas, is not very much applicable in mass spectrometer, because ultimately in any whatever property or whatever state your sample or your analyte is, you have to vaporize it and subject it into your mass spectrometer. So the option is, the answer is option B, that is the relative mass of atoms. So moving on to the next question, let us quickly move. In mass spectrometer, the ions are sorted out in which of the following ways? Is it option A, by accelerating them through electric field? Option B, by accelerating them through magnetic field? Option C, by accelerating them through electric and magnetic field? And option D, by applying a very high voltage. So I will tell you one thing, option D is not at all applicable, because by applying a high voltage, it is not possible that your ions will be separated, because in mass spectrometer, the basis of your separation is based on the mass to charge ratio. That is, your ions will be separated based on their masses as well as the velocity at which they travel into your spectrometer. So based on the mass to charge ratio, your sample analyte molecules or ions are separated. So option A is correct, by accelerating them through electric field. Option B is also correct, by accelerating them through magnetic field. Now both are correct. So option C, you can see, has both the above options, that is by accelerating them through electric as well as magnetic field. Now there is a reason for that, because when you're subjecting electric and magnetic field, the unwanted ions which do not have that particular mass to charge ratio are deflected, and only the ions having a particular mass to charge ratio are allowed to travel into your mass spectrometer, and that can only be possible with the aid of an electric as well as a magnetic field. So your correct answer is option C, by accelerating them through electric and magnetic field. Moving on to the next question. M+1 peak occurs for which type of isotopes? You have option A, 18C, you have option B, 34S, you have option C, 13C, and you have option D, which is 81BR. Now we all know the M+1 peak, which is nothing but it is that one extra ion is added to the molecular weight of your compound. So the molecular ion peak that you get in a mass spectrometer is always M+1. So suppose, for example, you have a molecular mass of 179. So if you're having a molecular weight of 179, so it is very likely because of the M+1 ratio that you are going to get because of the mass spectrometer. So basically your mass, that is the molecular weight, if it is 179, it is going to be 180. It is going to be detected as 180 on your on the molecular ion peak that you're getting. So that is always going to be +1 the mass of your +1 the original mass of your atom. So always 12 carbon, and it will always be +1. So you will always get 13C. So the correct answer is 13C. Moving on to the next. The deflection of positive ions formed in a mass spectrometer by electric and magnetic field depends upon which of the following? Is it option A, mass, option B, charge, option C, velocity? As I said, your ions are going to be separated based on the mass to charge ratio. So option A and option B is also the right answer, but option C is also correct answer. Why? Because ultimately it will depend upon the velocity at which your ions are going to reach your detector. So the lighter mass, suppose your analyte is having a lighter mass, or maybe you will have clusters of ions from a particular ion, because basically an analyte is a complex structure of multiple functional groups. So it is a possibility that you will get multiple peaks, that is multiple ions will be formed. Like you have the parent ion, which is the molecular ion peak, then you will have your other fragments, which are the daughter ions. So you will get multiple masses you'll get multiple fragments coming out of a single molecular entity. So they are all going to be separated based on their masses and velocity. So all the fragments with the least mass are going to travel faster because they are lighter in weight, and they will be deflected at a faster rate towards the detector. So mass, charge, and velocity, all of these three are the factors which is responsible for the deflection of positive ions. So I will select all of the above and move on to the next. You can see that I've already solved 5 questions in like approximately 10 minutes. So moving on to the next, which ion gives the molecular weight of the compound? As I said, the parent ion is called as the molecular ion, and the peak which you get of the molecular ion peak is nothing but the +1 molecular weight of the compound. So the option A, fragment ion, is not applicable. Option B, molecular ion, is the right answer. Rearrangement ion is also another type of a fragment ion which will be formed by a rearrangement reaction. So again, that is also not going to directly give you the molecular weight of the compound. So option C is not the answer. And option D, metastable ion, is also not your answer. So the only possible answer, you don't even have to look at the option C and D, because your obvious answer is option B. So let's not waste much time on this and move on to the next quickly. The ionization technique which is not used for volatile compound. So you have the following options you can see here. For option A is CI, that is the abbreviation for chemical ionization. You have option B, which is FAB, fast atom bombardment. Then you have option C, chemical, this is a CFI, which is also called as a chemical field ionization. And then you have option D, which is electron ionization technique. Now, basically, FAB, that is the fast atom bombardment, is the likeliest answer. Why? Because chemical ionization, chemical field ionization, and EI, which is option A, C, and D, are all used for volatile compounds. Now, there is a reason why FAB is not used for a volatile compounds. Why? Because FAB is a soft ionization technique and it is basically used for thermolabile compounds. So basically, if your compound is thermolabile, they will not require heat for ionization. So the basic procedure is that the FAB directly bombards the surface layer of the sample with a high speed directional movement of neutral atoms, ionizing the sample to form positive ions. So basically, because your analyte is thermolabile, it is not necessary that you can subject them to hard ionization techniques or other ionization techniques that may utilize heat. So that is the reason why the other ionization techniques are always going to be used for volatile. But FAB is the only technique which will be used for determining compounds that are non-volatile or derivatized, as well as some polymer compounds. And it is also very effective for determination of oligosaccharides, oligopeptides, oligonucleotides, and thermolabile organic compounds. Because oligosaccharides, oligopeptides, and nucleotides, there is a very high chances that they will be degraded if they are subjected to heat or harsh ionization techniques. So FAB is your answer. So moving on to the next. Which of the following statements is not true about mass spectrometry? You have option A, impurities of masses different from the one being analyzed interfere with the result. Option B, it has a great sensitivity. Option C, it is suitable for data storage. Option D, it is suitable for library retrieval. Now let us look at option B. It has great sensitivity. Yes, mass spectrometer is a very sensitive technique. You can even analyze analytes in femtogram as well as picogram and microgram levels. So you can go as low as a femtogram levels. So that is what is very sensitive. That sensitivity is nothing but the ability of any instrument to detect the lowest of the possible concentration of your analyte or sample. So that this technique is so sensitive that it can even detect very low levels of your compound. So option B is true. Option C, it is suitable for data storage is also true because you have a software for operating the mass spectrometry which stores and analyzes all of the data. And it is also suitable for library retrieval because if you have any past analysis in your instrument, you can look into it and you can retrieve data by going to the backup and everything. So all of these facilities are also available. So the only option which is not true about mass spectrometry is impurities of masses different from the one being analyzed interfere with the result. Now, why is it not true? It is simple. Mass spectrometry is unique to that particular analyte and will only detect that particular analyte of whose mass to charge ratio you need to find out. So basically, if you are analyzing something, if you know that you have to analyze a compound, even if there are impurities, the parameters of your mass spectrometer are set in such a way that the ions of the impurities will be deflected and only the ions having a particular mass to charge ratio will go to your mass spectrometer. So it is irrespective of any impurities that are present. It will only detect the analyte of interest because all the data that you have is going to be fed into your mass spectrometry. You are going to use a standard to tune your analyte in the mass spectrometer. Tuning is nothing but you have to set all the parameters on the mass spectrometer. That means when you're going to do an initial method development, you will find out all the multiple fragments, you will input all the masses of the fragments, the molecular ion mass and everything. So it is very unique to that specific analyte only, and impurities will not have any effect on your result. So option A is the only statement which is not true about mass spectrometry. Moving on to the next. Mass analyzer is similar to which of the following optical spectrometer? Option A, source. Option B, monochromator. Option C, detector. And option D, sample. The option A, source, is not the right answer. Why? Because mass analyzer is not related to anything or the source. So the source has absolutely no connection. The only thing which has a similarity, the only option here which has a similarity to a mass analyzer is monochromator. Why? Monochromator only allows a specific wavelength of light to be detected because it directs that particular wavelength of light. Similarly, a mass analyzer only allows a particular mass to charge ratio compound to be detected because it filters only that particular ions having that particular mass to charge ratio, and rest of the other ions are deflected and not detected in the mass. So the monochromator is the only option here which is having a similar activity like the mass analyzer. And the mass analyzer and the detector all means the same. Basically, a detector is also called as a mass analyzer. And option D, sample, is also not the right answer. So the only following options which is similar to an optical spectrometer and mass analyzer is nothing but a monochromator. So monochromator is your answer. Moving on to the next. Which species of the following is used to bombard the sample for which mass spectroscopy has been performed? We all know that a beam of electrons is subjected onto your sample. So it is you don't have to look at the other options. I can spot electrons here in option C. Alpha particles are not bombarded, neutrons are not bombarded, and protons are not bombarded. The only species that are bombarded on your sample in mass spectrometer is it is subjected to a beam of high energy electrons. So the option is C. So we'll not waste much time and move on to the next question. Which of the following detectors are used in mass spectroscopy? Is it option A, photomultiplier tube, option B, phototube, option C, photovoltaic tube, or is it option D, thermopile? Now it is not a phototube, it is not even a photovoltaic tube, but not even a thermopile. Why? Because the obvious answer is photomultiplier tube. What does a photomultiplier tube do? It detects the various ions and the electrons that are emitted out, and then because of the properties of the photomultiplier tube, it is able to detect all the ions present. So basically, photomultiplier in photomultiplier, the ions initially strike a dynode, which results in electron emission. These electrons then strike a phosphorus screen, which in turn releases a burst of photons, and these bursts of photons are detected. So in a photomultiplier tube, electron multiplier tube, it is basically an electron multiplier tube that utilizes the multiplication of electrons by secondary emission to measure the intensity. So basically the intensity or the mass intensity which is detected is because of this property of your photomultiplier tube. So moving on to the next. Which is a characteristic of fragmentation of the molecular ion of a carbonyl compound containing at least one gamma hydrogen? So moving on, we have the following options: alpha fission, beta fission, option C, McLafferty rearrangement, and option D, Retro-Diels and Alder rearrangement. Now moving on, option A, alpha fission, is not the right answer because the fragmentation of a molecule and of a carbonyl compound will not occur with that alpha bond breakage. It will not even occur with the beta bond breakage. Now what is going to happen in a McLafferty rearrangement? That is option C. McLafferty rearrangement is basically the fragmentation of a carbonyl containing radical cation via beta cleavage to produce an enol radical cation and an alkene. So the most possible way a carbonyl compound is going to undergo fragmentation is by McLafferty rearrange. Because why? Because a carbonyl compound is, because of the presence of the carbonyl compound, a beta cleavage is going to occur by the McLafferty rearrangement, and it is going to produce an enol radical cation and an alkene. So the answer is option C. Moving on to the next. The procedure for mass spectroscopy starts with which of the following processes? The sample is bombarded by an electron beam. Option B, the ions are separated by passing them into an electric and magnetic field. The sample is converted into a gaseous state. And option D is the ions are detected. It is very simple. I will arrange the chronology for you. Basically, the sample has to be converted into a vaporous state, or that is the gaseous state. After the sample is converted into a gaseous state, it is directed into your mass spectrometer, where then which is the next procedure which is happening, is the sample is bombarded by an electron beam. And after the bombardment of the electron beam, the ions are formed, and these ions are separated by passing them through an electric and magnetic field, and the ions having the required mass to charge ratio will be detected. So the very first thing and the start of the entire procedure is basically option C. The sample is converted into a gaseous state. And then the remaining of the procedure occurs where your sample is bombarded with an electron beam, then they are separated using an electric and magnetic field, and then they are detected. So moving on to the next question. We have, in mass spectroscopy, intensity of each signal represents what? Is it option A, relative abundance? Is it option B, base peak? Option C, parent abundance? And option D is molecular mass abundance. Now, we all know that in mass, there is going to be a single peak, which is going to be the highest intensity. But there will also be different other peaks also of the same analyte, but having a different molecular mass, because they are going to be the fragments of the parent molecule. So the relative abundance of a specific ion in a sample is calculated basically by dividing the number of ions with a particular mass to charge ratio by the total number of ions detected. So basically, what does a relative abundance tell you? It is nothing but a measure of how common or rare a species is relative to other species in a defined location or community. So basically, each signal will tell you the information about how much in quantity or how less in quantity the species are. So basically, a signal is nothing but the intensity in a signal is nothing but it is representative of a relative abundance. It is not a representation of the base peak. It is not a representation of how much of the parent is abundant, and neither it is a representing the molecular mass abundance. All it is representing is nothing but the relative abundance, that is how much of the entire entity, entire population of the ions are present. So it is basically the relative abundance. So moving on to the next, we have the main advantage of reflection of TOF analyzers, which is the time of flight analyzers, over linear time of flight analyzers of similar dimensions is that they have an increased resolving power. Is it option A true, option B false, options, and we have option C, which is option 3, and option D, which is option 4. So basically, the main advantage of a reflection time of flight analyzers over linear time of flight. What happens in a linear time of flight analysis is that the path is linear, but in a reflection time of flight analyzers, there is multiple reflections occurring while during the flight of the ion into the analyzer. So because of that, the resolving power is increased highly. So the answer is nothing but option A, which is true. Moving on to the next, who invented mass spectrometers? It is very simple. It is a very practical question and theoretical question, which when you will study, it is no one else but J.J. Thomson. It's neither Goldstein, neither Nikola Tesla, neither Einstein. Moving on to the next, by mass spectroscopy, which property can be identified of a molecule? Is it option A on functional group, option B on saturation, option C types of hydrogen, or is it D molecular weight? We all know that mass spectroscopy, the name itself suggests that they detect the mass to charge ratio, and it is giving information about the molecular weight. So the obvious answer is option D, molecular weight. It cannot be functional group because the information of functional group is basically can be detected with the help of IR or NMR spectroscopy, and saturation can be detected by UV spectroscopy, and the types of hydrogen again can be detected by NMR spectroscopy. So the obvious answer, the only spectroscopic technique which is capable of detecting your molecular weight is your mass spectroscopy. So you can see that we have quickly solved most of these MCQs in hardly around 30 minutes. Now, mass spectrum is obtained by plotting molecular weight versus peak height, concentration versus peak height, Concentration versus degree of deflection of ions, or is it abundance of ions versus the mass to charge ratio? Abundance of ion is nothing but your relative intensity, that is the relative abundance. So it is intensity versus the mass to charge ratio. So in the x-axis, you have the mass to charge ratio, while on the y-axis, you have the intensity, that is the relative abundance. So it is obviously the plot of abundance of ions versus mass to charge ratio. It is never the molecular weight versus peak height, because based on the mass to charge ratio, you will, and based on the intensity, you can find out the molecular weight of the compound. It cannot be concentration because based on the intensity, you can, the detector calculates and gives you the concentration. And that is the reason why even unknown concentrations can be detected. So option B and C is also not an option. I mean your answer. Moving on to the next. Which of the following statements about ion trap analyzer is correct? Option A, ion traps are beam analyzers. Option B, single ion trap analyzers are capable of tandem MS, that is MSMS. And we have option C, ion trap analyzers have very slow scan rates. And option D, ion trap analyzers require an ultra high vacuum. Ion traps are beam analyzers. Which of the following is correct? Is ion traps are not beam analyzers. So the first statement itself is incorrect. Option B, single ion trap analyzers are capable of tandem MSMS. Yes. Tandem MSMS means nothing but even if you're using a mass, that means you have an LCMSMS where you have an hyphenated technique of your tandem mass with liquid chromatography, or you have gas chromatography with your tandem mass. So basically single ion trap analyzers are used for tandem MSMS. That is, tandem mass is nothing but your MSMS. That means your detector will also be a mass spectrometer, and that is basically your ion trap analyzer, and it will also have a quadrupole analyzer, and it will also detect, and it will also ionize, it will also deflect separate your ions and also detect. So basically the option B is your correct answer. Ion trap analyzer has a very slow scan rates, which is incorrect. It has a very fast multiple scan rate. So it can scan multiple ions simultaneously at a very less amount of time. And ion trap analyzers require an ultra high vacuum. It's not true, because they can work under medium vacuum conditions. They do not need a very high vacuum for your ions to be detected. Moving on to the last question, you can see that in 30 minutes, I have solved almost 19 questions. In McLafferty rearrangement, elimination of neutral molecules takes place from hexane, amide, benzene, aldehydes. Now, the obvious answer is that in McLafferty rearrangement, elimination of neutral molecules takes place always from the benzene functional group. So always remember that in McLafferty rearrangement, it is always the benzene functional group which helps in the elimination of neutral molecules. So this will be our answer. So I have attempted all of the questions in around 30 minutes. So I will submit the test, and these questions were very easy and very much theoretical. So we didn't have to use much of our logic or strain our brain, as the MCQs were comparatively very logical and direct. So I'm going to submit the test, and that would be all. I hope this session helped you approach the MCQs more easily. And you can see that we have solved 20 MCQs in a matter of 30 minutes. So you might have around 125 questions in your GPAT examination. So time is of the essence, and you have to try to attempt maximum questions in limited time without getting a negative marking. So you will always attempt the questions which you're confident of first, and leave the ones which you're not very confident for later, so that you can utilize the remaining of your time by eliminating the options and selecting the very closely likely options that you feel is. So that is all for today. Thank you, everyone.